Finishing up 3.5 today, we're going to take a look at a couple other small things. We looked at division and multiplication algorithms last time. And the next thing that we're going to take a look at is some application problems that involve multiplication and division. And as we look at these application problems, we will use some of the methods, the algorithms that we explored last time. So here's Juan. Juan saved $53.40 in 3 years. If he saved $95 per month in the first year and a fixed amount per month during the last 2 years, how much did he save per month the last 2 years? So this kind of has a feeling like maybe it should be back in section 1.2 or 1.1 where we were doing problem solving, okay? And it could be there. I mean, there's nothing wrong with that being a possibility. So part of what we're doing here is going to involve obviously multiplication and division, or it wouldn't be in this section. But there is some problem solving to be involved here as well. So as you take a look at this problem, what do you think you might try first? What might be a first step for this problem? 95 times 12. I agree. How did you get that, Hannah?
95 per month first year.
Okay, so it says he's going to save 95 per month the first year. And again, part of the reason we're doing this is practice using other algorithms. So let's give this a try, and somebody suggest another algorithm that you might like to try here. Do you want to do partial products? Do you want to do lattice? What would you like to try? Or expanded algorithm, that's another one. Lattice. Thank you for giving us a place to start. Okay, so with lattice, we put the 9 and the 5, or the 1 and the 12, either way, along the top, and then the other one along the side. We create a grid, and it says it's a 2 by 2 multiplication problem. It will be a 2 by 2 grid. We split it in half and in half again, okay? Each diagonal gets split. And then we do multiplication in each box along the row and column that they're on. So the first top left corner would be 9 times 1, because it's 9 above and 1 to the right, so that's a 9 and it goes here. And then we're going to have 5 times 1 to the right, and that's going to be 5. And then we're going to multiply 9 times 2, which would be 18. So 1 in the top left, 8 in the bottom right. And then 5 times 2 would be 10. So 1 in the top left, 0 in the bottom right. Then we're going to extend our diagonals. And we start in the bottom right-hand corner, adding. So 0, that's an exciting addition problem right there. My next diagonal is 5 plus 1 plus 8. 14. So I write down a 4 and I carry a 1. 1 plus 9 plus 1. 11. And you could write the 1 and carry the 1. You could also just write 11 at this point because there's nothing in the next column's diagonal, right? So the answer ends up being 1140 here. Now, be careful as you're working these word problems because there might be multiple steps involved, and in fact there are. What did we find by finding this 1140? How much he made or saved the first year, right? So what are we supposed to be finding? Fixed amount for the last 2 years. All right, so we're not done yet, is my point. What would we do next then with this 1140? What information will we do with it?
1140 or 5,000.
So the 5,340 minus the 1140. And this is a fantastic subtraction problem because there's no borrowing or anything going on. So I'm not going to belabor the point because there's no equal additions. There's nothing to be done here. You can go from left to right or right to left. You're going to have 4,200. Then what? We want to divide it by 24 would be a possibility. You could divide it by 2 and then divide by 12, which might be easier for kids to actually think about that way, right? It might be. The 24 is not bad. The problem with division by 24 is that we don't have 24's tables. But that's okay. For what we're going to do, we're going to use a different algorithm then just to give ourselves practice with that one. So we had 4,200. We don't know tables of 24's. So we're going to practice repeated subtraction, okay? All right, so repeated subtraction is the idea of using the number that you're given, in this case the divisor, the 24, with zeros. So this is the biggest 24 with zeros following it that I can subtract. 4,200 minus 24. And if I subtract that, what do I get? 1800. Can I subtract, and this was 24 times 100, by the way, that's what I just did. Can I subtract 2400 again? No. So what would I subtract next? 240. And the reason or how I get 240 is 24 times what? 10. Okay, so what's 1800 minus 240? 1560. Can I subtract 240 again? Quite a few more times actually, huh? If I subtract 240 again, what do I get? 1320. Can I subtract 240 again? Yep. What do I get? 1080. Another 240. 840. Another 240. We're getting close, right, to the end of the subtraction of the 240s. 600. 240 again. All right, I gotta make this smaller because I'm running out of space. Okay, 240 again. Whew, man. No more 240s, right? But can I do 24?
Yes.
I can. And 24 again comes from 24 times 1. I almost started out this question by saying you guys are going to hate me after this one. All right, what is 120 minus 24? 96. And again?
72.
And again?
48.
Oh, and then 2 more times evenly, right? 24, 24, 24, 0. Whew! Man, repeated subtraction was a booger on that one, wasn't it? Really was. How many hundreds did we have? 1. How many tens? 7. And how many ones?
6.
I think it's 5. Let me see. 1, 2. Yeah, I have 5 on the screen. So the answer would be 175 written with the $sign, right? That's how much you would be saving per month for the last 2 years to have achieved that end result. Let's take a look at another one. Dan. Dan has 4,520 pennies in 3 boxes. He says there are 3 times as many pennies in the first box as the third, and there are twice as many in the second box as the first. How much money does he have in each box? So what do you think you might try to do first on the problem? Think like problem solving. Like section 1.1, like 2 months ago. Well, dividing by 3 would be taking the pennies in essence and making 3 stacks of them. So there are going to be 3 stacks, but dividing by 3 would make them equal in size, and we don't have equal size stacks. My gut says I should draw 3 boxes. You guys good with that? So we are going to make 3 stacks of things, 3 boxes. And he references how many he has in each box based on which box he's talking about. Here's my first box, here's my second box, and here's my third box. What are the statements that he makes about these boxes and how many pennies they each contain and so forth? Okay, so whatever he has in the third box, we don't know. So could we let that be X or some other variable? then how many does he have based on that in box 1? 3x. So whatever quantity we have in box 3, we've got 3 times that many in box 1. What else do we know? We have twice that in box 2. Twice what? Twice box 1. So 2 times box 1, and box 1 is 3x, means how much do we have in box 2? We actually have 6x in box 2. So our ratio of these boxes is actually like 1 to 3 to 6, right? So for example, if I had 10 coins and 10 pennies in box 3, I would have 30 pennies in box 1 and 60 pennies in box 2. Is everybody following that okay? Okay. So, but I don't have that many pennies. I've got a total of 4,520 pennies. So how can I use that 4,520 pennies and the information I've written sort of inside my boxes to figure out the actual number of coins in each box? Well, that would mean that that's how many coins I have in each of it. That sounds better. So what do I want to put equal to the number of pennies? All right, Hannah says 10x, which is from the 3x, the 6x, and the x, right, Hannah? And that would equal my 4,520 pennies. So she's right, that's already 10x. So then what? Divide by 10. What is x? 452. 452 is x. Now, we need to be careful that we answer the question asked. There are 2 things to be aware of. This says how much money. I mean, and you could say, 4,000 or 452 pennies. That's okay. That's sort of an awkward way of describing money. We don't usually talk about money in terms of pennies. We talk about it in terms of dollars. So it would be a little bit more natural to say that in box 3, we have $4.52 instead of saying 452 pennies. Even if you said 452 pennies, I'm not gonna gripe at you. I mean, that would be fine. It would be okay. It's just a little bit less natural. How do I figure out how much I have in box 2 and box 1? Okay, so if we take 452 and we multiply by 3, right? That would be our value in box 1. And what would we get for that? $13.56. And then what would we do to get the number or the value inside of box 2? You could just double that, absolutely. So if you're working sort of as a continuous line of thought, you can take 1356 and double it to give you what? 2712 is correct. And this would be the amount that we have, or the value, how much is in each box. Let's take a look at another one. A student observes that 39 plus 41 is equal to 40 plus 40, and asks if 39 times 41 is equal to 40 plus times 40. How do you respond? Now, we did a question that had one of those how do you responds as your homework question for today. It was the student that did the adding one business and short one and stuff. Short one, not adding one. They wrote down short one. And I said, how do you respond? And one of the things that I first said when I looked at it with you and looked at how do you respond is, first thing you need to know is whether or not it works. Right? Did their method actually work? Did they get the right answer? So the first question is, does 39 times 41 equal 40 times 40? No. What does it equal on the left? What is 39 times 41? Thank you. Yes, 1,599. What is 40 times 40? 1,600. So the most direct way to respond to the student is to show them that the arithmetic, multiplying these out, these don't equal each other, right? So the answer is actually no, this does not work. You can't add one to one number, subtract one from the other number, and it actually worked out the same with multiplication. So continuing along that line, we have student number 2 in the next example. Another student observes that 39 times 41, that's what we just found, 1599, equals 40 times 40 minus 1. Now take a look over there. Is that true? Yeah. If I took 1 away from the 1600, would I have this 1599? I would. He also found that 49 times 51 is equal to 50 times 50 minus 1. And he wants to know if the pattern continues. Can you always do that, right? Can you take 1 away from one number, add 1 to the other number, multiply, and then just subtract 1 off? And if it does, what does the relation have to be between the two values in the equation? It seems like, at least the 2 examples he's given, is that they look like they're two away from each other, right? 1 more and 1 less than what you've done. Now, it's a good question of whether or not that's just because he chose these examples, or whether that's always true, right? Does that have to be true, in other words? So it might not be a bad idea for us to try something different. So what if we did, say, 39 times 51? We make them further apart, okay? And then if I add 1 to that and subtract 1, so if I did 40 then here and 50 here, will it work? So I'm still doing the adding 1, subtracting 1. I just started with the numbers further apart to see if that's really actually have to be true or if it was just true because that's what he picked. Do you guys understand why I'm testing something different? Okay, so let's check and see what happens. What is 39 times 51? 1,989. Excuse me, and then what is 40 times 50? What is it? Oh, well, before we subtract the 1. I think you already did that. Is it 2,000?
Yes.
Okay. So are these 1 apart? Like if I subtract 1 from this, will I get the other one? No. So it certainly seems like I can't just arbitrarily make them further apart. So the relationship business may be the case that they need to be 2 apart. Does it matter? The other thing that you probably should notice is that he picked ones that are exactly apart from powers of 10, or not powers, but multiplications of 10, right? He chose something nearby 40. He chose something nearby 50. Is that special? Does that have to work that way too? Well, we think that the being 2 apart might have value, but what if I did, say, 42 and 44? Right? Those are still 2 apart. Agreed? So what's 42 times 44? Okay, and then I add 1 to one, subtract 1 from the other one so that they both become 43s. What's 43 times 43? 1849. So do they fall into his same pattern? They do. It looks like they still work, right? So maybe it doesn't really matter if they're close to like a 40s or a 50s or a 60s, that they're close to something ending in 0. It's convenient to do that, but maybe it doesn't always matter. So how could I find out in general? Well, it sort of looks like that it's true for all the numbers that are 2 apart, right? It seems like it might be true. So what if we try that? What if we let our numbers be 2 apart? So in particular, we can let one be x and the other one be 2 more than x. This would be a way of arbitrarily writing down numbers that are 2 apart, right? Kind of like when we were doing the problem over here. Oops, sorry, one more back. How do we write down the numbers that double and triple things and so forth? Well, we sign it x and we double it or we triple it or we, whatever to it. Same idea. Okay, so then we would take one and we would add 1 to it. And we'd take the other one and we'd subtract 1 from it. And that's the process he was doing with actual numbers. Now with algebra, if you were to distribute this, what do you get? Not 2x, x squared, yeah, and then plus the 2x after that, yeah. X squared plus 2x. What happens if you FOIL this? First, our question is whether or not they're 1 apart at the end. So we're gonna deal with the minus ones in a minute here. Yeah, so just hold tight. We'll put the minus one on, but I'll just put it on at the end. If you don't want to put it on the end, you want to put a minus one here, you can do that. I think it's easier, for me at least anyway, to just think about it being one apart when we're done. First terms, x times x would be x squared. What happens when I do the inner and the outer terms? I get 2x. And what happens when I do the last terms? Plus 1. So compare these. How are they different? That 1 at the end of the second one, right? They're off by exactly 1. So if I were to subtract 1 from the second expression, I would have the first expression, right? So the question asked is, does this pattern continue? Is this always true? And the answer is yes. If the original two numbers differ by 2. Or you could say they're 2 apart from one another. You know, if the second number is 2 more than the first, any of those kinds of expressions, then yes, it will always work. And that is the relation that it has to be true. They have to be different from each other by the value 2. Okay. So here's what we're going to do. I'm going to finish this lesson. We will do the group work for it on Monday next week. Okay. Unfortunately, that means that you won't get your papers and stuff back in time for the test that we were talking about doing and so forth. Okay. I mean, not talking about, we are doing it, but the timing will work out a little bit differently, but we won't do this group work today. Okay. Sound good? All right. I want to talk to you about some different kinds of mental math. We did mental math with addition and subtraction. Now we're going to do mental math with multiplication and division. Okay. So mental math, this is called front-end multiplying. So front-end multiplying means taking the first digits and separating them out, kind of like breaking them up by place value. For example, the 4 here represents 40, and I can do 40 times 5 in my head easier than I can do 46 times 5 in my head. What's 40 times 5? 200. And then I can do the 6 times 5, which is 30. What's 200 plus 30? 230. Now, again, we talked about this before, but let me just reiterate. I know that the whole point of mental math is it's supposed to be done in your head. You're writing down what your head's doing so that I'll be able to see it on paper. That's all. So if you can't do what you just wrote down on paper, then it would not be mental math that you used. Okay? Let's talk about compatible numbers, another strategy we saw before. When we looked at compatible numbers before, our goal to making them compatible was that they added to 10. That's really what it was. Well, when we're multiplying them, our goal is to make them a value with a 0 in the ones place. For example, 4 times 5 is very friendly, but 4 times 8 is not. 4 times 5 is 20, and it's got a 0. It's really just a 1-digit number with a 0 next to it, right? That's really what it is. But 4 times 8 would not be convenient because it would be 32. I really get a legit 2-digit number. And I can do the same thing by grouping the 10 and the 5 together. I'm sorry, the 2 and the 5 together to make it 10. And even better is that the 20 times the 10 is another number that's got a bunch of zeros in it on purpose, right? So what's 20 times 10? 200. And then don't forget the 8. We haven't dealt with him yet. 8 times the 200 then would be... No, times, not addition. 1,600. So the goal is to do as much of the multiplication where you get zeros in it as possible. Okay, keep multiplying until you end up with no other way to multiply that doesn't give you a zeros in the tens place or zeros in the hundreds place or something like that. Okay, 0 in the ones place. Compatible numbers give us digits of zeros. Thinking money. Every time I do this one, people forget this one. And this is a super cool method for doing this. It's called thinking money. Now, just like with every multiplication or every mental math strategy, it doesn't work for every number, okay? So when does thinking money work? Well, it works when you're multiplying by 5s and 25s, okay? So the fact that we're multiplying by 5 means that thinking money might be a good strategy. And what we're going to do is we're thinking this 5 as a nickel. Why would I do that? Why would I think of a 5 as a nickel? Because it's 5 cents. A nickel's worth 5 cents. Okay? So what we're imagining here is that we have basically 46 nickels. And aside from the fact that it would have a heavy jar of change if you had 46 nickels, it's not super simple to multiply those two numbers together. Okay, now it's not horribly awful, but the more nickels you had, the more awful it would be. So I think that it would probably be easier to turn my nickels into dimes. Why would it be nicer to have dimes instead of nickels? There's fewer of them. There's something else too. It's a 0. It's a 1 0, right? And dime is worth 10 cents. And multiplying by 1s and 0s is easier than multiplying by 5s. So if I had 46 nickels, how many dimes is that?
Oh, 23.
23 is correct. How'd you get that, Hannah? You cut it in half. It takes 2 nickels to make a dime, right? If it takes 2 nickels to make a dime, then 46 divided by 2 would be the number of dimes I have, right? 2 nickels equals 1 dime. So I have 46 nickels, then I have 23 dimes. What's 23 times 10? 230. Without a doubt, that's a head problem, right? At that point, 230. Now, what we really did, just so that you can kind of get a sense of it, is that we divided this number by 2 and we multiplied this number by 2. You could do that to any number. You could divide one of them by 3, multiply the other one by 3, divide one of them by 5, multiply the other one by 5. Like, you could do that process. It wouldn't hurt anything. It's just that it works really nicely on this because it's dimes and nickels to think about it and to get numbers that are convenient to multiply together. I mentioned that it worked well for 25s as well. Why would it work well for 25s? 25 is a quarter, right? So this is a quarter. So this is equivalent to having 44 quarters. When you have whole bunches of quarters, what do you usually turn them into? You turn them into dollars, right? So if I had 44 quarters that I was turning into dollars, by the way, dollars are worth 100, right, in terms of pennies or something like that. It's 100 cents. How many quarters, from the 44 quarters, how many dollars would that be? It'd be 11. This is $11. So how did you really go from 44 to 11? What'd you do? You divided by 4, and the reason you did that is because you multiplied by 4 to go from quarters into dollars, right? 4 quarters in a dollar. So you divided the 44 by 4. Multiplied 1 by 4, divided 1 by 4. Okay, so then what's 11 times 100? 1100. The multiplication ends up being very nice. All right, the next two are for division. 6318 divided by 9. Breaking up and bridging, or breaking up the dividend is another way to do this one. So in other words, it's very nice because 63 nicely goes into 9. I said that wrong. 9 goes very nicely into 63, and 9 goes very nicely into 18. So the idea of breaking up and bridging is breaking this up so that you have 6,300 plus 18. Or you can write it, I think your book writes it like this, where it just sort of draws a line in here. Put a plus sign or draw a line, whichever you prefer, and you divide by 9. So what is 6,300 divided by 9? That would be 700. And then what is the 18 divided by 9? 2. And then if you combine those, what do you get? 702. So you're breaking them up. Now, the reality is that this number can be done very much the same way, but you don't break it up quite the same. 5 does not go into 4. 5 goes into 25, but 5 does not go into 4. Yet, if you break it up that way, so that you get 400 and you get 25, will 5 go into both of those? Yeah, it will. So you very much are doing the same kind of thing. You're breaking it up. It's just that it's not as readily visible that how you're breaking it up. How will the 5 go into the 400? How many times? 80 is right. Good. And then how many times will 5 go into 25? 5 for a grand total of 85. Very nice. Okay, let me do my estimation problems. They're really fast, and then we'll finish this up, okay? We've got 386 times 4. If it says estimation, it means you're not going to multiply 300 times 4, 80 times 4, and 6 times 4. That would be the exact value. Estimation means doing something in an easier way, right? Where we get an approximation for an answer. So what we're going to do is we're going to do the 300 times 4, and we're going to do the 80 times 4. We're just going to do 2 digits worth. If you had a 6-digit number, you'd still do the first 2 digits worth times the value. What's 300 times 4? 1200. And what's 80 times 4? 320. And if you added these together for an approximation as an answer, what do you get? Approximately 1520. Is it exact? No, because we ignored the 6. But it's a pretty good approximation. And we can do the same kind of thing for the division example with estimation here with compatible numbers. 4132. That actually evenly divides by 4. Okay? We haven't talked about divisibility rules, but it does. It evenly divides by 4. But that aside, the whole goal is to say that it actually is easily divided, right? I see it readily. What could I approximate 4132 to, a nearby-ish value that's easy to divide by 4? 4,000 would be a good choice. If you wanted to go with 4,400 as a slight overestimate, that would be okay. But something with 4s in it would be nice, right? What's 4,000 divided by 4? 1,000. So this is approximately 1,000. Or if you decided to round up and you did 4,400 and divided it by 4, you would have got 1,100. So your approximation would have been an overestimate at 1,100. Mine was an underestimated 1,000.